Okay, so we have defined the energy momentum tensor for the electromagnetic field. Let me point out a few things. This is a problem that you will verify, but if you actually find the T00 component and write it in terms of the electric field and magnetic field, you will see that this is the following quantity. You should recognize this from your E&M course as nothing more than the energy density of the electromagnetic field. There's another problem where you will compute T0I. And when you do that, once again, you will find that this is E cross B, the ith component of this. These are things you will verify in your homework. But you should recognize this. This is proportional to the Poynting vector. In fact, the Poynting vector S is 1 over mu 0 E cross B, and also from E&M. So we're just recalling a few facts because I'm trying to put the pieces of the electromagnetic or the energy momentum tensor in terms of physical quantities, physical components. If you recall, this is nothing more than 1 over c squared s. So when you combine all of this, so this is the energy density you will see that Pi, the ith component of the momentum contained in the field, is nothing more than T0I over C. So if I were to write T mu nu, I would do the following. I would write this as the energy density. Whatever, by rho c squared, I mean, I don't mean just the electromagnetic field. For anything, it's the energy density. In the case of the electromagnetic field, it's this one. And if you look at the 0I component, it is c times p, so maybe c times the x component of momentum, c times the y component, c times the z component of momentum. The T mu nu, you will see, is symmetric. Well, just by looking at the expression, you see it's symmetric. We talked about this. Therefore, this also has to be. Okay? So, using the techniques that we are about to do shortly, and it's in the notes, I would like for you to verify this, you will see that the diagonal terms is nothing more than the pressure. And over here, let me just call it, for example, sigma. I'm just calling it sigma 1, 2, sigma 1, 3, and I'll tell you what they are. Sigma 2, 1, sigma 2, 3, sigma 3, 1, sigma 3, 2. First of all, like I said, we have done this one, and we have done this one. Using the techniques that we're about to talk about, you need to verify that whatever I'm talking about here is true. It's in the notes. You just have to follow the argument. But sigma ij is the shear of the electromagnetic field. So in words, they would be, it's sort of a weird quantity. Sigma ij is ith momentum flowing out in the jth direction per unit area per unit time. just go through the rest of my notes and fill in this part, okay? And again, sigma ij, just like T mu nu, is symmetric. And as you spend more time with it, you will see why this is, in fact, the case and why it's needed. Okay? Now, because of this statement and this statement, I'm going to define a quantity that looks like a vector, but it's a non-vector in a vector's clothing. Lowercase p. It's a 4-tuple because it has a mute index. And I'm looking at this guy right here, and I'm going to define this as 1 over c T0I. T0 mu. Okay? Clearly, this is not a vector, a 4 vector, because this is just a 0th component. And we know components of tensors don't transform as vectors. Okay? So this is not a 4 vector. But if you look at this, and looking at this and this, you will find that this is energy density over c, and this is momentum density. Now, why would we bother defining something like this? We can easily create a conserved quantity. So I'm going to define P mu. Distinguish one from the other. This one has a little flag on the top. It's lowercase p. This is uppercase p. This is only true for a certain inertial frame. You have fixed the inertial frame, and then you take this P mu and you integrate over all space. What I will show is this is in fact a conserved quantity. What I'll show is that if I take the time derivative, this is ddt, I get that to be 0. Therefore, the 0th component can be total energy divided by c, and the spatial components can be the total momentum. This is not very difficult to follow, but very quickly, here it is. So, dp mu dt is equal to, I bring the derivative inside, it becomes a partial derivative, dt x, and this you can see very nicely becomes 0 mu over, there's a c, so it very nicely becomes a ct dqx. Now recall that the energy momentum tensor is divergence free. This implies that this is equal to minus ddxi ti mu dqx. I'm going to integrate over all space, and then this becomes a boundary integral because this is a divergence theorem for each fixed mu. When I do so, I get ti mu dA, but the ith component dA. And suppose I have fields over here and I go infinitely far away where there is no field, therefore there's no energy momentum tensor, and this is as r maybe goes to infinity, this will go to 0, and that's exactly dp mu dt. So this guy is concerned. What is more interesting, and we won't do this, what is more interesting, and you might want to consult Weinberg's book on gravitational cosmology. He has a nice argument that uses delta functions. When you integrate this guy, this big p mu is indeed a 4 vector. Any questions about the energy momentum tensor? I think what I want to do is give you some more examples of energy momentum tensors that are particularly important to us. So you will see very soon, we're going to start gravity on Monday. We'll be done with this very quickly. You'll see very soon that the Einstein equation, just like electromagnetic fields are sourced by charge and current, the Einstein equation is sourced by energy momentum tensor. So if the energy momentum tensor is 0, we call it a vacuum solution. So for example, black holes, at least the ones we study, are made of vacuum. It's just space and time, right? So the right-hand side of the Einstein equation would be 0. In this course sequence, we study basically 2 types of solutions to Einstein's equations. One is the black hole, and the other is cosmology. In cosmology, of course, the universe is filled with galaxies and whatnot. We're studying the very large-scale structure, so you and I don't affect the fate of the universe. In fact, stars don't affect the fate of the universe. It's clusters of galaxies that would be a point in the scale we're studying. But nonetheless, what we have is sort of a fluid of galaxies, right? And so for that, we need to do a little bit of studying about, it is fluid dynamics in one way, but what the energy momentum tensor of a fluid would look like, okay? So with that in mind, in your homework, I've assigned, just to gain mathematical familiarity with energy momentum tensor, we've already seen the electromagnetic energy momentum tensor. I've given you the Klein-Gordon energy momentum tensor and asked you to show that it's divergence free and so on and so forth. Okay? So today we'll try to study fluids. Okay? So to begin with, the non-interacting dust. And this is to build fluid models. So, I mean, perhaps the physics of it would be very uninteresting. It would be just galaxies peppered in the universe with no pressure or anything like that. We'll get to pressure very soon, but we're just building the model. So, you know, you would have just mass everywhere in a region, okay? So I'm going to consider a rectangular box. And I'm going to go, this dust varies smoothly. Now, there may be regions where these dust will have velocities, right? And, I mean, it could have velocities anywhere. But what I'm going to do is I'm going to pick one point over here, right in the center, and jump into a Lorentz frame where the dust is at that moment, at that instant, it's just static. So you just have just dust sitting there. We're going to get it to move. That's easy to get things to move in relativity. You just do a Lorentz transformation. So that part is free. Okay? So if I look at that block, the mass contained in that block is going to be rho 0, let me explain, delta x, delta y, delta z. And I would call this density times volume, and I would call this the rest density. Okay? In this frame, locally, the dust is not moving. Yeah?
Dust is not moving, but there's change in dust through the X phase to Y phase.
Sorry, what's that?
So the idea of this is that the change in X in this case is dust going through the X phase, right?
No. So we have at one instant sort of frozen it and jumped into a Lorentz frame where at that point in your cube, the dust is not moving.
Okay.
Yeah?
Changing the size of the cube in this case. Is that what the delta is?
Oh, no. Oh, the mass contained in that cube. So to get the total mass, you have to integrate
This
it.
is small mass.
Yeah. Sorry. Yeah. So this is a cube with length, delta x,
Delta y.
delta y, delta z. Yeah, mass contained. What I would like to know, well, what would it be in a frame where it is moving? So that's easy to do. I will pick the factor will be the same. The charge could, the dust could be moving in any direction, right? We'll, at that place, orient it so that the dust is moving in the x direction. Okay. When it moves in the x direction, what happens to the volume?
Volume stays the same. Volume of the cube.
Correct.
Still be delta x delta y.
Well, no. There's, in the x direction, there will be a length contraction. So, jump into a moving frame. First of all, we can agree that in the x direction. What is the relationship between x and delta x? Length will contract. Correct? So I can write delta x as gamma correct? That means, and I can subsequently write this as rho delta x, delta y, delta z, and clearly rho equals gamma equals 0. So density transforms under a Lorentz transformation. What is it? What bothers you, Jackson? If you see a moving meter stick, how long does that meter stick?
Well, it's as long as 1 meter.
No, it's not. Assume it's not going slow. This whole course is in the business of things moving fast.
It's smaller than a meter.
It's smaller than a meter. Yeah.
So, can gamma technically be multiplied by delta x bar, delta y bar, or delta z bar in this case?
Listen, I'm just.
I understand. I understand how you're doing that, but I mean, like, if rho is just equal to gamma.
Well, so in any frame, you would want to call density to be mass per unit volume. So we would call this the moving. I could put a bar here if you want, but I'm not. But I'm just I'm distinguishing this by rest density, this by any density. Do you know something that transforms under Lorentz transformation with just a gamma?
Time?
For velocity frames. Let me explain. If you look at an object at rest, okay? This is the 4 velocity. This is rest. This is C, 0. Correct? In any other frame, U equals C gamma gamma. Correct? So we have this nice way to see something that transforms with a gamma. We want conservation of mass, regardless of who's observing. The mass contained in a certain volume of fluid. If it's the same volume of fluid, we want the total mass to remain the same. You know from E&M or what we have discussed before, the continuity equation. Continuity equation, we saw that effect divergence of T mu nu equals 0. From that we get momentum and energy conservation. So we want to create a current. Yeah. So I'm going to define a current. To be rho 0 times u mu, which is the 4. So now u is going to be, this particle will have some u. I'm going to define, and this u may be smoothly varying. By the time it's over here, it may have changed its angle slightly. So, but it's a density with a proper velocity. And then, because, well, we're not completely done. U has this extra C in there. We don't want the C, so this is, if you will, the matter current density. But I want conservation of matter. So we'll try this and then we'll require d mu j mu equals 0. Let's see what happens to this requirement, consequence. Well, mass, you would want to define it to be, what is it? Rho e cubed x. Normally, correct? Okay, well, let's see what happens. So I'm going to look at the rate of change of mass. 1 over, because of this, 1 over c, I'm just going to put this, and I'm going to do this. J0 d cubed x, that's equal to 1 over c. I really don't much care about the z, the c, and this becomes a partial with respect to t, j0 d cubed x. Well, that's convenient. This is ct is the 0th component. And so that is equal to minus divergence. Is that true? Because what does this say? This is dct j0 plus dx jx plus ddy jy plus ddz jz equal to 0, or this becomes, as you mentioned yesterday, I'm going to integrate over all space where matter ceases to exist. So imagine a universe where there's mass everywhere, but if the entire universe is filled with mass, you cannot even define mass. Total mass is infinity. Imagine if mass is decaying far away. And then when you go far enough away in your integral, is there any mass over here? So this is J dot dA. And some, if you want, R approaches infinity. So this is, you will get this to be equal to 0. That means ddt of, no, integral of J0 dqx is a constant. Constant in time. That means integral of rho dv, or rho J is rho 0 gamma, which is rho in that frame. So the point is, this continuity equation allows for what? So this is the consequence we're considering. Allows for mass to be conserved. In E&M, what does the continuity equation conserve? Because you have the same equation in E&M. d rho dt plus divergence of J equals 0. Remember the continuity equation? That's how we got charge conservation.
Charge.
Yep. In E&M, you conserve charges. In the case of a fluid, you conserve the mass of the fluid. But the mass of the fluid can be conserved due to the divergence of, for divergence of J being equal to 0. That's fine. But we didn't start off trying to create a mass current. We need an energy momentum tensor. So in this case, we'll set define equals rho 0, rho mu, divided by what? Figure C squared. Yeah, no. This is fine. I don't have to. So you in the rest frame, listen, you can see in the rest frame, U equals C0. So then T00 equals rho 0 C squared, MC squared. So this is indeed the energy density. Right? Just like the electromagnetic field. This is how one creates an energy momentum tensor. We try to create something that's a tensor whose zeroth component, 0, 0 component is the energy density. That's a good way to guess to create an energy momentum tensor. In this class, for example, for E and M, I just gave you the energy momentum tensor. We didn't start off with, but if you recall back in E and M, we knew the energy of the electromagnetic field, and then we looked at how that changes, because energy momentum tensor is divergence free. And then we back created. So that is what we're saying. This is mass. I mean, the zero component of this is energy density. Energy density is proportional to mass density, mc squared. We know the continuity equation will conserve the mass. So there's a good chance of this being a divergence-free tensor. It is a tensor. Rest mass, the rest charge density, or rest mass density is a scalar because it's rest mass. These are 4 vectors. So this will transform exactly like a tensor. But we require d mu t mu equal to 0. We want it to be that, because it is that kind of stuff that would conserve energy and momentum, as we have seen already. Okay? Are we good? You guys are unusually quiet. Yeah? Well, let's take this is just straight out taking derivatives. Tell me if you follow. Oh, I missed what I've added is u nu. Now, there are 2 ways to do this. Suppose it satisfies this fluid or the non-interacting dust satisfies the continuity equation. Guess what this is going to be? Suppose the non-interacting dust we're trying to create a fluid model for, if it satisfies the continuity equation, what is this going to be?
That should be
0.
0.
Now this guy is the proper time derivative of the 4 velocity. Is that the 4 acceleration? That is the definition of acceleration. If you have non-interacting dust, nothing is acting on it. These are free particles. What is the acceleration of the free particle? 0. So these both are 0, so that indeed you get this equation. There are 2 ways you can think about it now. You can forget the continuity equation, and you can require this. Then this implies the continuity equation. Because this has to be 0 and this is 0, therefore this will be 0. Yeah? There are two ways to think about it. The continuity equation motivated the energy momentum tensor to be divergence free. But if you say the law of fluid dynamics is the law of conservation of the energy momentum tensor being divergence free. This is a weird divergence. This is not the divergence that you're used to, but it sort of looks like the divergence. It is in fact thought of as a 4 divergence. If it is divergence free, then you get the continuity equation. So we can scrap the continuity equation and say for a non-interacting dust, this is the energy momentum tensor, and this is the equations of motion. Because it gives you that its current is divergence free and so on and so on. Unfortunately, this is not the universe we live in. Just galaxies just sitting there. It doesn't do that, right? It evolves. The galaxies interact with each other. There's gravitational pressure on these guys. If one set of galaxies will go this way, the others get pulled, or the same kind of fluid effect starts. Now, if you put all sorts of terms into the energy momentum tensor of a fluid, oh gosh, it can get crazy. It can have shear terms like we've seen, viscosity, all of that. People do that to get refined modeling. Turns out those kind of things we cannot even observe. But what we can observe is the pressure in the universe. That becomes very important. So the static, just dust just sitting, or just non-interacting dust doesn't sound very reasonable. First of all, non-interacting doesn't sound very reasonable. If you leave a block of wood, there's not much, nothing much interesting. You come back tomorrow, it's right there, yeah, sure. That is not the universe we live in. So, we have to let it interact. This becomes very important when we talk about cosmology. Here we start with, and I will write this as a matrix. I'm doing this in the rest frame at the moment because I know how to write things in the rest frame. And then if I leave everything as a tensor, that's going to be the tensor. So again, rest frame, the advantage is what? That's the 4 velocity. So at that moment, at that point, charges are not moving. How do we get charges to move? Well, that's easy. Lorentz transform. I keep saying charges. I mean mass density. Yeah. So I would want rho c squared. Perhaps even rho 0 c squared. And these are momentum, but it's in the rest frame. Gosh. Over here, for what term is this? This will be shear. 0, 1, 0, 1, 2. Single 1, 2, for example. What is the diagonal entry? But I'm going to write something and I'm going to erase, so don't write it yet. What's the diagonal, spatial diagonal in energy momentum tensor? Pressure. Right? Like I said, don't write it yet. I'm not studying any fluid. I'm studying the perfect fluid. They don't exist. They're like perfect students. Completely theoretical. All right, Gracie, we'll have an exception for you.
That's my guess.
I mean, she was like, surprised, oh my goodness, could that be? So,
Right after saying it doesn't exist.
right. But one way to make things perfect is pressure is just pressure. There's no preferred direction in the universe, right? That's not where we're headed towards. The universe is left-handed. It may be true that there might be some preferred symmetries. But that doesn't appear to be the case. Nor does it appear that, at least, we don't want to worry. You don't want shear in your homework exams anyway. So the universe may be, and in a rest frame, in one immediate sense, it'll look like this, if rest frames exist. So what I'm going to do, I'm going to write this, well, no. I'm going to try to make a tensor out of it. And component by component, you tell me if it works. I'm going to write T mu, and gosh, I need this for sure. U takes care of the C squared, because U has that C squared over here in the zero component. That part is taken care of. I need to somehow handle pressure. So pressure, what I'm going to do is pressure eta mu nu. Why? I know this is a tensor. I know this is a tensor. Plus, I mean, these are really the tensors I know. Let's see if that works. This takes care of rho c squared, correct? Because U only has the C term. Now, let's see what happens to the 1, 1 term. When mu nu is 1, 1, then what happens? This is 1. And then I have over here C squared over C squared. That's another one. No, sorry. For the spatial part, that is 0. Yeah. Yes. So this works in the rest frame. So you require that for a perfect fluid. This works in any frame. Definition of a perfect fluid in any frame.
Even Lorentz transform?
Yeah, you will change. Now you will have XYZ component.
But it still works.
So it works. Well, it's a tensor. That is a tensor which agrees with this in the rest frame. That's the whole point. We want a tensor that agrees with this tensor when U is given by that.
And the fact that it agrees with that tensor means
Yeah.
that it will agree with any tensor. Or well, it will be. It will make a tensor.
If a tensor is equal to another tensor at a point in one frame, it's going to be equal. If they're equal in every frame.
Even if there's
The components may not be the same, but they transform into each other. Hold on. If you have electric field is a bad. Yeah, okay, fine. We won't do Lorentz transformation. We won't do any time-dependent transformation. If you have electric field at some point in a Cartesian coordinate system, what is the electric field at the same point in a spherical coordinate system?
the exact same.
It's the same thing. It's the same electric field. Vectors go into vectors. It's the same vector. The components might change. In Cartesian coordinates, it's Ex, Ey, Ez. But in spherical coordinate system, it's Er, E theta, E phi.
They should be equivalent.
This should be equivalent. So the entire tensor agrees at every point at the rest frame. So you jump from another, one point to another, you pick a new rest frame. They agree. At every point. The entire tensor. This should be non-zero, everything else will be Oh, well, and this should be P, everything else should be 0. That agrees. Therefore, it must be true all the time. What about the equations of motion? We don't know. So we require, that is the equations of motion for a perfect fluid. Whatever that comes out to be. That is not today's word. Are we good? Okay. Last section of this chapter. Energy conditions. Just because you write out a certain energy momentum tensor, it doesn't mean that they are physically relevant. I mean, this one just seemed totally made up. How can fluids obtain, do this be the equation of motion of a fluid? It seems like you have to study fluid dynamics, work it out and all of that, then get results. But relativity as an extra word, it has to satisfy causality. So let me again harken back to what we know. See, we know that in general, what is this? This is the energy density, right? For example, what is T00 of electromagnetic field? It's 1 over epsilon naught, no, 1 over 2 epsilon naught E squared plus 1 over 2 mu naught. Energy is roughly this mc squared. It's positive, or at least it's non-negative. This has to be greater than 0. And this, so we want T00 to be greater than 0. For who? For any observer. So first, let's start with this rest observer. T00 is equal to T, because this is not a scalar. This is a component of a vector. So that doesn't mean anything. One person's zeroth component is not the other person's zeroth component. I should write it as a true scalar. So isn't that true? Because what is u nu? Minus c, 0, 0, 0. But minus c times minus c again becomes, I get a minus c from here, I get a minus c from here. So I get c squared, then I cancel the c squared. This is true for a rest observer. Are all observers resting? No. So this is called, definition, this is the weak energy condition. We require that every T mu nu when contracted with any observer. So what is an observer? A future pointing time-like vector. Correct? In general. So for any future pointing time-like observer. By continuity, this should be true for like-like observers as well, because time-like approaches like-like. This is the weak energy condition. We require all T mu nu to satisfy this. Now, there's another thing. Although this is not a 4-vector, we talked about this energy momentum object. This is 1 over c t 0 mu. Can I write this in an invariant way for a rest observer? Except do I need to do a c squared? It's 1 over c anyway, but u nu has a c, so I have to divide it by. This is to be an energy and momentum. Momentum and energy has to be future pointing and causal. Correct? That means this has to be what? A future pointing causal vector. What's that?
I thought it wasn't a 4.
No, it's not. It has to be a future pointing. Oh, no, hold on. What is this? This is no longer T0 mu. Is this a 4-vector? What happens if you take tensors and contract?
Vector. It is a vector now.
Yeah, it is a vector now.
So it becomes a vector if it's for a rest observer.
It becomes a vector when you, right. Let's do it that way. Yeah? So that means this has to be a minus, I don't care about the c squared, t nu mu nu has to be a future pointing causal vector. Are all observers rest observers? Dominant energy condition. We'll say that an energy momentum tensor satisfies the dominant energy condition if minus T mu nu W mu is FPC for any FPT, I can even say. Will show that for the perfect fluid, this is not true for any fluid. There's a condition. I think rho c squared plus 3p must be greater than 0 or something. 3p because there are 3p's there, right? condition must be satisfied. So for all physical energy momentum tensor, for now, we will require the dominant energy condition. Dominant energy condition will imply the weak energy condition. Okay, there are other energy conditions. There's a strong energy condition and a null energy condition. Null energy is already taken care of. Instead of time like, we're saying cost. So there's a strong energy condition. That comes about when Hawking started studying the singularity theorems. It's only true for things that satisfy strong energy conditions. I'm done. I'm done with the chapter. Any questions? Start working on the homework problems. Let me know when you want the exam. Conversely, not conversely, but in preparation for the exam, we can have a homework discussion session.
Are all of the homework problems